this lecture, we will be discussing on something known as a ring. So what is a ring? A ring is also a set. So the ring is actually a group, but it has some additional properties that are not generally associated with groups. Okay? So a ring is a group with some additional properties associated with it. Okay? What are these additional properties? We'll see. How do we denote a ring? A ring is denoted by the letter R and two operations. One is the plus and one is the multiplication operation denoted by dot. Both are binary operators. A ring denoted by the set R and two binary operators. One is the addition denoted by plus and the multiplication denoted by the dot. Okay. Is a non-empty set equipped with, again, basically it's a non-empty set equipped with two binary operators. Okay. What are the two binary operations? Addition and multiplication. Okay. Such that the following properties hold. Number one, R is an abelian. But under what operation? Because there are two operations to it. So it is an abelian group under the plus operation. With E as the identity element. Okay. So what are the properties that should actually hold? R should satisfy the closure property, the associativity property, existence of a unique identity element for the plus operation, that is E, and existence of a unique inverse of all the elements, unique inverse corresponding to each element in R for the plus operation. Okay, and because it is an abelian group, the binary operation is commutative. Okay, basically x plus y will be equal to y plus x. Okay, so the first thing, R is an abelian group under the plus operation. Next, for all x, y, z, in the set R, the associativity property is satisfied for the dot operation. Okay. That means x being multiplied to the multiplication of yz is same as xy multiplication being multiplied to z. Third, there exists I should say a unique element denoted by its symbol double scripted 1 in the set R such that for all x in R, okay, whatever x you take, 1 multiplied with x is same as x multiplied with 1, and both of them result in the same vector x. Okay. So this is similar to the identity element for the plus operation. The identity element were denoted by 0. Similarly, here when in case of the dot operation, if the argument is a vector and the other argument is this double scripted 1, then the output of this operation is the other vector. Okay. So this is also known as the multiplicative identity element. Okay. So the first property that you saw is with respect to the plus operation. Then in addition to this, there are two more properties which are on the dot operation. The fourth property is a property that is associated with both the plus and the dot operation. So for all x, y, z in R, if you take the addition of x and y and multiply it to z, it is same as multiplying x to z and y to z and taking a plus operation on the results. Okay. Similarly, if you multiply x to the plus operation on y plus z, it is same as x being multiplied to y and x being multiplied to z and then the plus operation on the result. Okay. So this is known as distributivity. So if you notice the notice the dot operation gets distributed over the plus operation. Okay. So what do we see is a ring is actually a abelian group with a unique identity element corresponding to the plus operation. Then you have the associativity with respect to the dot operation, existence of a unique multiplicative identity for the dot operation, and the distributivity that you have with respect to the plus and the dot. Okay. So if a group satisfies all these four, then that group is termed as a ring. Okay. Now, if for a ring this particular condition holds. Okay. Take any pair of any element, any two elements from the ring. The product of x and y is the same as the product of y and x. Okay. Basically, the dot operation is a commutative operation on the ring. Okay. This is a commutative operation. The dot operation itself is a commutative operation. Then the ring is said to be a commutative. Okay. So if you remember in the group, if the commutation operation with respect to the plus operator holds in a group, then the group is known as a abelian group. Similarly, in a ring, if the commutation operation holds with respect to the dot operator, it is known as a commutative ring. Please note that in a ring, the plus operator is already a commutative operator. Okay, because it requires R to be a abelian group to qualify as a ring. Okay, so this commutative nature of the dot operation, if it is there, if it is associated with the ring, then the ring is a commutative ring. Okay, can you give me some examples for a ring? Can you think of some examples? We'll see some examples for you. I'll start with set of integers with plus and dot is this a ring? Set of integers with plus and dot operation. So is this a ring? You know that this is the set of integers with the plus operation is already abelian group. And just check for the remaining three properties. So is associativity true for the multiplication operation? The answer is yes. Is there a unique element? The unique element in this case would be 1. Okay. Yes, there is a unique identity element, multiplicative identity element rather. And does the distributive property hold? Note that there are two distributives. One where the dot operation is being distributed on the plus operation occurring on the left, and one where the dot operation is being distributed over the plus operation occurring on the right. Okay, both are distributed. So, is it true for integers? Again, the answer is yes. Okay. So the set of integers with the plus and multiplication operator is a ring. Similarly, what can you say about a set of real numbers? Set of real numbers is denoted by the double scripted R and the two operators. Okay, so it's a ring. Similarly, a set of rational numbers with the addition and multiplication operation is also a ring. Even a set of complex numbers under these two operations, the addition and the multiplication operation, is also a ring. Are these commutative ring? Basically, does commutation hold under the dot operation? And the answer is yes. So all these four are commutative rings. Okay. Now set of n cross n real matrices. One can denote it with this. Set of n cross n real matrices. Under the plus with the binary operators plus and this. Okay, so we are talking of, is this a ring? This is definitely a abelian group under the plus operation. Associativity holds for matrix multiplication. Even the distributivity holds from both sides. Okay. Is there a unique identity element with respect to the multiplication operation or the dot operation? Answer is yes. It's the cross an identity matrix. Okay. So this also is a ring. The question is this a commutative ring? So it's rather putting it like this: is the matrix multiplication commutative? Answer is no. This is a ring, but not a commutative ring. Okay. Examples 1 to 4 are commutative. What can you say about the set of polynomials in T denoted by the double scripted P? The polynomials are what? Polynomials are basically also a set of real polynomials. Polynomials in T meaning AIT T to the power I equal to 0 to n. Okay. And this n can be 1, 0, 1, 2, 3, 4, infinite n. Not talk of infinite, n is a finite number. And AIs belong to R. The idea. Is this with the plus and the multiplication operation? R ring. Can you verify if the set of real polynomials in T is a group or not? See, it is actually a group. In fact, it is a abelian group. And if you verify, I suggest that you verify this. Try to do it formally. But you can also establish that the associativity for the dot operation holds, and the unique identity element for the dot operation is nothing but 1, and the distributivity also holds from both sides. So this actually is a ring. In fact, is this a commutative ring? The dot operation is commutative here. So this is also an example of a commutative ring. We will stop here.